The North American P-51 Mustang arrived with immense promise, featuring a beautifully streamlined airframe that looked fast even sitting on the tarmac. However, in its initial configuration, powered by the original Allison V1710 engine, the plane was plagued by a critical performance flaw. It simply couldn't compete with the German fighters at high altitudes. While the Mustang was a capable low-altitude reconnaissance and attack aircraft, its maximum speed and ceiling dropped off dramatically above 15,000 feet, leaving it exposed and ineffective against the high-flying Focke-Wulfs and Messerschmitts. This limited operational ceiling meant that the beautiful, long-range plane could not fulfill its destiny as a high-altitude bomber escort, the most crucial role demanded by the Allied command. The pilot's verdict was harsh. The early P-51 was a beautiful failure, an aircraft with world-class aerodynamics that was being held back by insufficient power delivery and a severe lack of high-altitude performance. The engineering challenge became existential. How could they unlock the obvious potential of the airframe without a complete and costly redesign? The problem wasn't the wing or the fuselage. It was how the engine's considerable horsepower was being converted into actual forward thrust, an issue that pointed directly to the most scrutinized, yet often overlooked, component in the entire aircraft. The solution to the P-51's altitude struggles arrived in the form of a captured British innovation, the legendary Packard V1650 engine, an American-built, license-produced version of the British Rolls-Royce Merlin. This new engine was an absolute monster of power, delivering massive horsepower smoothly and consistently into the high-altitude regimes where the original Allison faltered. Swapping the engine transformed the P-51 overnight, giving it the necessary altitude, performance, and speed to finally take on the formidable German fighters on their own terms. This marriage of the sleek North American airframe with the potent Merlin created the foundation for the Mustang's legend. However, this massive infusion of horsepower created an immediate, critical engineering dilemma that the original propeller system could not solve. The four-bladed propeller was now tasked with handling significantly more twisting force, or torque, than it was ever designed for. The original, simpler propeller blades could not efficiently capture and transfer the sheer rotational energy being produced by the Merlin, leading to wasted power and limiting the ultimate top speed the aircraft could achieve. A truly fast airplane requires a propeller that can efficiently slice the air at high RPMs without vibrating itself apart or turning the engine's incredible power into unusable drag. The engineering principle was simple but unforgiving. To fully translate the Merlin engine's explosive power into the maximum possible forward speed, the propeller blades needed to be optimized for extremely high speeds and efficient operation at thin, high altitudes. The conventional propeller design was hitting a bottleneck. Its blades were starting to encounter the phenomenon of compressibility, where the tips of the blades approached the speed of sound, creating shock waves, generating massive drag, and resulting in tremendous inefficiency. This effect caused the propeller to essentially waste a large percentage of the Merlin's potential energy. The German engineers had long struggled with this same problem, often favoring smaller, lighter propellers that sacrificed efficiency for simplicity. The American design teams, however, recognized that the propeller was no longer just a simple spinning paddle. It was a highly complex aerodynamic surface. They realized that a traditional, stiff, 2- or 3-bladed propeller was physically incapable of managing the Merlin's power and the high-speed air compression simultaneously. A new radical design was needed, one that was inherently more complex, more highly stressed, and which conservative engineers immediately warned was too fragile for the rigors of combat flight. The solution championed by the bold engineers, a specialized propeller division, often working against conservative estimates, was the introduction of a new, massive, 4-bladed propeller design. This propeller was no ordinary wood or fixed-pitch design. It utilized highly complex, broad, and slender aluminum blades that were engineered to fine tolerances. The very characteristics that made them efficient, their relative thinness and their complex, automatic pitch-changing mechanism also made them appear structurally delicate and too fragile to conventional engineers accustomed to simpler, sturdier designs. This new propeller was designed to solve the compressibility issue by using its 4 broad blades to efficiently absorb the Merlin's torque and distribute the workload. Crucially, it employed a sophisticated constant speed mechanism that allowed the pitch of the blades to be continuously and automatically adjusted in flight. This fragile-looking complexity allowed the propeller to maintain optimal efficiency whether the plane was climbing steeply, cruising at low altitude, or screaming toward its maximum speed at 30,000 feet. It was the mechanical sophistication of this design that finally unlocked the Mustang's maximum speed potential. The new 4-bladed propeller design was necessary primarily to manage the immense rotational force, or torque, delivered by the 1,500 horsepower Packard Merlin engine. Standard propellers lacked the surface area and advanced pitch control to handle this sudden burst of power efficiently, meaning much of the engine's work was simply being wasted, creating turbulence and vibration instead of forward thrust. The new design overcame this by adding a 4th blade and significantly increasing the total surface area, allowing the propeller to effectively bite into the air and transfer that massive torque into usable thrust, minimizing slip, especially at higher speeds. However, controlling this tremendous force was where the fragility came into play. The new blades had to be engineered to incredibly fine tolerances to prevent destructive vibrations that could tear the propeller apart. The sophisticated constant speed governor, the automatic brain that constantly adjusted the blade angles, was a delicate, complex piece of hydraulic machinery. If this fragile mechanism failed, the blades could fly apart or go into flat pitch, instantly destroying the engine and the plane. It was a calculated risk, embracing complex, highly stressed engineering to achieve power that was simply impossible with simpler, more robust designs. The true secret to the propeller's success was not just the number of blades, but the constant speed mechanism that controlled the pitch. The angle at which the propeller blades cut through the air is critical. In a traditional propeller, the pitch might be fine for climbing, but terrible for high-speed level flight, leading to severe inefficiency. The new system was a continuous miracle of engineering. Its hydraulic governor constantly sensed the load on the engine and automatically adjusted the blade angle, ensuring that given X's into the vestiges, Merlin always operated in its most efficient RPM range, regardless of whether the pilot was climbing, diving, or cruising. This constant automatic adjustment made thousands of times per minute meant the engine was never fighting the propeller. When the plane dove, the pitch would automatically increase, like shifting to a higher gear, to prevent the blades from over-revving and becoming inefficient. When the plane climbed, the pitch would decrease, like a lower gear, to maintain power. This delicate, continuous optimization was the mechanical sophistication that finally allowed the P-51 to translate its new Merlin power into sustained, high-speed performance across all altitudes, fundamentally solving the propeller bottleneck identified by the engineers. The moment the redesigned P-51, now fully integrated with the massive new 4-bladed propeller, took to the sky for high-altitude testing, the pilot realized the engineers hadn't just fixed a flaw, they had created a new kind of machine. At altitude, where the original Mustang had wheezed and struggled, the new version, designated the P-51B-C, accelerated effortlessly. The sophisticated propeller was efficiently carving through the thin air, pulling the fuselage to speeds previously thought unattainable for a propeller-driven fighter. The testing confirmed the audacious claims. The new Mustang could now sustain speeds nearing 440 miles per hour at 30,000 feet, firmly putting it in the same class as the best German interceptors. The test reports were ecstatic. The new propeller completely eliminated the high-altitude performance drop-off, maintaining the Merlin's power and efficiency deep into the stratosphere. The flight characteristics were completely transformed, smooth, stable, and incredibly fast. The risk associated with the fragile hydraulic propeller system was instantly justified by the raw performance data. The Mustang was no longer a beautiful disappointment. It was now a genuine, high-speed, long-range threat capable of dominating the skies over Europe and later, the Pacific. When the P-51B C models finally hit operational service, the German pilots were completely unprepared for the sheer speed and endurance of the new American fighter. The combination of the Merlin engine and the efficient four-bladed propeller system allowed the Mustang to achieve speeds peaking near 490 miles per hour in level flight, a velocity that often surpassed the capabilities of the German interceptors at the altitudes where bombing missions were taking place. This was a direct result of the propeller's ability to efficiently manage the engine's power without hitting the compressibility bottleneck that plagued other designs. The new P-51 became a monster, capable of escorting bombers deep into Germany and sustaining high speeds throughout the entire engagement. German pilots, accustomed to easily shaking the older, slower Allied fighters, were suddenly confronted by a fighter that could not only keep pace, but often overtake them. Even in a high-speed chase, the fragile propeller design had delivered the overwhelming performance advantage the Allies desperately needed, transforming a talented airframe into the legendary long-range predator of the air war. The fragile four-bladed propeller, born of necessity and initially met with skepticism, was the simple yet sophisticated piece of engineering that finally unlocked the P-51 Mustang's full potential, securing its legendary status as the most effective long-range fighter of World War II. The propeller division's bold decision to adopt a complex, highly stressed design was a direct, successful challenge to the conservative engineering wisdom of the time. This single component, with its continuously adjusting pitch and superior aerodynamic surface, solved the crippling propeller bottleneck, allowing the mighty Packard Merlin engine's full 1,500 horsepower to be translated into sustained, clean forward thrust rather than being lost to vibration and drag. The result was a fighter capable of dominating the skies at over 490 miles per hour, far surpassing the performance of its original design. The legacy of this engineering gamble is profound. The P-51, once a flawed design, became the indispensable protector of Allied bomber streams, flying deeper into enemy territory than any other fighter and racking up an unparalleled number of kills. The fragile-looking complexity of the propeller was, in reality, its greatest strength, demonstrating that a fighter's true performance is often determined not by its engine's raw power, but by the efficiency of the most overlooked components. The propeller transformed the Mustang into the decisive, high-altitude monster that effectively neutralized the Luftwaffe's defense, ushering in the final phase of the air war over Europe and securing air superiority for the Allies.